my presentation, I will be talking about defects in molecular orientation in thin organic films. And before I start showing you my results, let me start with a little motivation why we are studying the molecules and especially the molecular orientation. So small organic molecules, also together with polymers, are perceived as a very promising candidate for the organic-based electronics. And here, in this concept, the standard inorganic semiconductors should be interchanged by small molecules that have also semiconducting features. Well, small organic molecules have specific issues that are distinct from the inorganic atoms or inorganic semiconductors. What you can see here, what strikes you the first, is that they are anisotropic, especially when talking about the rod-like molecules. And the anisotropy means that they have different properties in certain directions. So, and this is used for organic-based applications. For example, here you can see the organic field effect transistor, where the higher carrier mobilities were obtained when the molecules were oriented in the standing up orientation, so the carriers were more effectively driven between the source and a drain. Can you hear me? I'm not sure. Okay. On the other hand, when you look at the organic LEDs, they obtained a higher efficiencies when the molecules were oriented in the lying down configurations. So from these two pictures, you can imagine that the molecular orientation is a very important parameter. So you wanted to have in your layer, organic layer, you want to have just a certain one only orientation of your molecules. And the defects in the molecular orientation will deteriorate the efficiency of your devices. So, basically, in our group, we are growing the organic layers, and the technique we are using is called the organic molecular beam deposition. In fact, it's a very simple vacuum-based technique where you have a crucible that you fill with organic molecules in the form of powder. In this case, we used as an example, it's a diindapyroline, very promising molecule for optoelectronic purposes. And then you heat up your crucible and the molecule starts to evaporate, and they evaporate on the substrate of your choice. In this case, we use the molybdenum disulfide, few layers of molybdenum disulfide, which is very interesting semiconducting material. So as you can see from a simple AFM image, these molecules do not form like a continuous layer, but they form like an island type features. So here in this AFM image, you don't see the molecules themselves, but the islands or the monocrystals that are composed of the diindapyroline molecules. This type of growth is very typical for low-dimensional substrate like graphene or molybdenum disulfide monolayers. What is also known that because of the van der Waals interactions between the molecules and the substrate, the molecules are typically oriented in the lying down configuration. But this AFM image doesn't show you, so we needed to perform another measurements, and in our group we do a lot of X-ray scattering, and we use the Grayson incidence geometry. So for those of you who are not familiar with X-ray scattering, in this geometry we use a very small angles between the incoming X-ray light and the substrate, so the angles are typically 0.2 degrees. And with this technique, we are very successful in obtaining the molecular orientation. As you can see here, this diffraction is typical for the lying down orientation of the molecules, but as we were scanning through the sample, Also, an indication of a standing up orientation was present. So the situation looks like this. We have regions with lying down orientation, but there are also regions with standing up orientation. And unfortunately, this technique is not very good because the spatial resolution is not good and the X-ray scattering in general. So we were not able to obtain the domain size of the different molecular orientations. So this is the part where the s-SNOM come into play. And first, what we needed to do prior to the actual experiment and measurement, we needed to find the wavelength where the response of these independent molecules would be the greatest. So we measure the nanoFTIR spectra, and you can see that the material has the highest absorption around 1450 reciprocal centimeters. Just to show you, we also did a calculation, the DFT calculation, where we calculated as well the IR spectrum, and you can see that there is a pretty good match between the absorption peak for this molecule. In fact, this molecule was calculated, or these spectra were calculated for the single molecule in vacuum. So now we have the wavelength that we can tune our lasers so we can perform the s-SNOM measurements. And in fact, that's exactly what we did. So as you all know, we are getting at least 4 channels from the s-SNOM measurements. So the first two are the standard AFM, where the amplitude is proportional or tells you something about the topography, whereas there is also mechanical phase that tells you about the mechanical properties of your sample, like stiffness, adhesion, deformation, whatever. And then there is the s-SNOM signal, which has also an amplitude, which is proportional to the reflectivity, and absorption, that is, or the s-SNOM phase, or the near field phase, which is proportional to the absorption. Typically, what we found out in articles is that the orientation of the molecules is obtained from the absorption. So when we look at our pictures, we were extremely excited because you see that the phase has different height or different magnitude in the center of the island compared to the edges. So we were like, hey, this is great. We're having a different orientation of the molecules at the edges compared to the center of our island. When we look at the reflectivity, we didn't show any such, indication, but then we looked at the mechanical phase and said, yeah, the molecules are probably oriented in a different manner because we also have a different mechanical, different phases on the edges. So we performed the peak force tapping measurement, which tells you something about the mechanical properties of the sample, and unfortunately, we didn't see any differences at the edges and at the center of our island. So at this point, we started to be very suspicious that there might be something going on that is not directly connected with the orientation of the molecules, and as we're not experts in AFM measurements, we had to go through the literature and found this article that calculated the how the amplitude of the AFM is changed, how the amplitude changes with the distance from the sample surface and the AFM tip, and also how the phase changes. And from these two pictures, you can see that the amplitude changes linearly as your tip is going further and further from the surface. On the other hand, the phase is changing not linearly. So we thought, okay, so probably the phase of a s-SNOM wouldn't be the greatest parameter for telling something about the molecular orientation when you have non-flat surface and the change in the topography is abrupt. So that's why we only use the near field amplitude. This is another measurement at a different position on the sample. So this one was scanned closer to the edges. And again, you can see the molecular islands. But here now, you can see that we have two distinct signals. Some islands, and when we merge the topography with this near field amplitude, you can see that we have two types of islands. One of them, they're a little bit higher and have a lower signal of the reflectivity. And some of them, they are a little bit shallower, I would say, a little bit wider, that have a much higher reflectivity. Okay, then we did more and more analysis. So we were going through our sample and measuring in different places. In fact, this is the one that I already shown, and this is the one that was measured in the middle of the sample. And again, we were getting better statistics, and we were able to obtain or to see that we only have two kind of signals. So so the islands that are taller and have higher reflectivity signal, and the islands, there are less of them, but have a higher reflectivity signal. And this is in accordance with our previous study that the majority of the molecules adopt the lying down configuration, like shown here, whereas there are some areas where the molecules adopt a standing up orientation, like here. And I don't know, we were surprised, like why in this case we have lower signal than in this case. So, and in the previous talks they will mention that, for example, for this molecule at this wavelength, when you excite the molecules start to vibrate in the direction of the molecule, which means that there is a molecular dipole that is oriented along the long side of the molecule. And when we have an incoming light, it also induces a dipole moment in the AFM tip, which is also aligned along the AFM direction, AFM tip direction. So now these two dipoles interact with each other. In case you have the lying down molecules, like here, the interaction is smaller, so the scattering, the amplitude of the scattering light is smaller when you compare it to the case when these two dipoles are aligned. So that's why we're getting these two different signals. And when we did the ratio between the amplitude for the standing up and lying down orientation, we got the number around 2.4. Well, 2.4, that was surprising to us, because I would say when you have like a big signal and a small signal, the number should be at least order of magnitudes larger. So we did the calculations, and we did the DFT calculations that were done in collaboration with Zdeněk, and we calculated all the modes, and we find out that in the vicinity that we not only have one mode that was measured before, but we use a different technique, and we have also this mode that is somehow connected or is overlapping at the frequency that we are measuring. And this mode has a perpendicular orientation of the dipole. And we were able to calculate the dielectric function, where the diagonal components are proportional to the orientation of the molecules with the incoming field. So when we calculated the ratio between the dielectric X and dielectric function Y, we could obtain a good agreement with our experimental results. Okay, so with this, I would like to conclude my talk. So as I was showing, we were able to determine the molecular orientation with a very high resolution, and we found out that the molecular orientation is encoded in the near-field amplitude with minimal perturbation, whereas the near-field phase contains artifacts related to structural variation or topography edges. So thank you very much for your attention.